do just a quick slide of about me. So I'm a 6-year grad student in the UC Berkeley Astronomy Department, and I study black holes. And I'll tell you a little bit more about that later. Some of the telescopes that I get to use in my work, I'll tell you about this later more too. One of them is the Hubble Space Telescope. And this telescope has been orbiting Earth in space for the last more than 30 years. And another telescope that I get to use is the Keck telescopes in Hawaii. They're 10-meter telescopes on top of Mauna Kea, and they're currently the biggest ground-based telescopes on Earth. And one of the great things about being a student at the University of California is that we get to use this telescope for our research. And some other things I like to do with the astronomy department, we have a lot of public outreach events. And so several times a year we have big events for lots of like families and kids. And one of them is the Bay Area Science Festival. And each year it's held in AT&T Park now. It's called in San Francisco, the baseball field. And so that's here. And one of the demonstrations we do is we have a mirror, and we use this mirror. It's a parabolic curved mirror. Use it to focus sunlight at a very particular point, and then we can light marshmallows on fire. So that's what this picture is from. And it's related to astronomy because telescopes, they have big mirrors. They collect and focus distant starlight. And so this is just for a slightly different purpose. So that's a little bit about me. Now I'd like to tell you a bit more about black holes and my research. So before we talk about black holes, though, I'd like to talk about where they come from. And so black holes, they sound like science fiction, but they're real objects. And when very massive stars die, they produce black holes. And stars are bright because they're burning a lot of energy. And this energy creates outward pressure that keeps the star from collapsing. And so when a very massive star runs out of fuel to burn, they don't produce the necessary pressure to support themselves. And so it's like those bouncy castles. When the generator stops, there's no pressure to hold the walls anymore, and so it collapses. And so similarly, when a massive star runs out of fuel to support itself, it'll collapse and die. And when the star collapses, it forms an object that's so dense that nothing can escape its gravitational pull, not even light. And so if light can't escape from an object because it's so dense, then we can't see it. And so that's why these are called black holes. And so in summary, black holes are produced when very heavy, massive stars die and run out of energy to support themselves. And then these black holes are formed from these dead stars. And so there's different kind of configurations or varieties that black holes can be found in. And one of these is called a binary black hole. This is where you have two black holes and they're orbiting each other. And as these two black holes orbit each other, they produce something called gravitational radiation. And so the system is losing energy. And so the black holes, as they orbit each other, they get closer and closer and closer. And eventually they get so close that they merge. And when they merge, they produce a really large signal of gravitational waves. And so this was actually discovered very recently in the last about 10 years. The first detection was in 2015. And it was detected by something called LIGO, the Laser Interferometer Gravitational Wave Observatory. And so that was the first time gravitational waves from a black hole merger had been detected. And in the last 8 years since, now they've detected way more systems, probably over 100 at this point. So another type of system black holes reside in is when a black hole is paired with a star. And so when the black hole and the star are really close to each other, the black hole can actually eat the star, eat material off the star. And when it does this, this is the star, this is the black hole. You can't see the black hole, but there's glowing stuff around. And that's because as it's eating the material off the star, the material is it's kind of orbiting the black hole in the disk. And when more material hits that disk, it glows. And that glow in X-rays allows us to find these black holes. And so the glow in X-rays is how we actually first knew of the existence of black holes 50 years ago. These X-rays were seen, And from that, it was deduced that there's black holes in our Milky Way. Sometimes, actually more often, the case is that the black hole and the star pair are a lot farther apart. And so in this case, the black hole is too far away to eat material off the star. So instead of seeing X-rays, the black hole and the star just orbit each other quietly. And because we can't see the black hole, really all you see is the star. And the way you can figure out there's a black hole there is the star appears to be orbiting something unseen. And so if you can observe a star that seems to be orbiting some unseen object, that tells you that there's a black hole there. And so these have also been found recently in the last 3 to 4 years, and it's been enabled by really large surveys observing millions and even billions of stars. And so they can search for these stars orbiting invisible companions. And the last one, which is the one that I'm most particularly interested in studying, is called isolated black holes. And so all these other type of black holes had some companion, whether it was another black hole or a star. But isolated black holes, kind of its name suggests they're alone, they're by themselves. And so they don't have a companion. And so the question then is, if they're dark, how can we find them? And so the way we can do this is using the fact that black holes can bend the path of light rays that move close to them. And so one of the predictions of Einstein's theory of general relativity is that space and time are all mixed up together. And things like black holes, which have really strong gravitational fields, can bend and warp that space-time. And so light usually travels in a straight line, but if the gravitational field is very strong, like right next to a black hole, its light will get bent and it'll get deflected. And so that's kind of what's illustrated here. So to visualize this better, I'll show an animation next, but before I play the animation, just want to outline what's going to happen. So there's this pink camera here, and that's like the observer, you or me, on Earth, and what we see. Far in the background, there's a star. It's just by itself out there. It's not doing anything. It's not moving. And then there's going to be a black hole that's going to move between us and the star. And so it's going to move up across the screen like that. And the thing to remember is that the star is not moving. But because there's a black hole in front that has really strong gravity, as the light from that star, it would normally just go straight and then to your eye. The black hole is going to bend the space-time in between us and the star and cause the star to look like it's in 2 different places at the same time and change its brightness. And that's because what would normally just be light going from the star to us in a straight line is getting bent and refocused along our line of sight. So let's see if we can play the animation. Okay, I'll play it several times. So this is the black hole, and you can see it's moving. And then here, these are what we see. Remember, this is kind of tricky. The star is just still in that one position that I showed earlier. These are what we call the images produced by the bending of the light, the lensing. And you can see that there's 2 images produced. Just keep playing it. And as the black hole is moving, the brightnesses of the images change. They both get brighter, and then one starts to get dimmer as the black hole keeps passing by. At the beginning, this one's brighter and this one's fainter. Then they both get brighter, and then they both fade, and it appears to just go back to one star. When the black hole is really, really far away, there's essentially no bending of light, and then it just looks like there's one star, as there really is. Now I want to draw your attention to the bottom corner here. This is kind of like a bird's eye view. This is what we would actually see on Earth. And so the thing is that you can see that there's 2 stars here. There's only one star here. The reason is because on Earth, we can't see those 2. Let me just loop it like that. We can't actually resolve these 2 images. It's like if you're driving a car and the car has 2 headlights and the car is really far away from you, those images of those 2 headlights just blur together to one headlight. It's only when the car is really close to you, you can see the 2 headlights. And so it's that resolution. We can't resolve these 2 images. So what we see on Earth instead is just one single object that seems to brighten and dim. And the other thing is this star appears to change its position. So I'm leaving my cursor fixed here. You can see that it moved from where the star was as the bending of the light occurs. So here, this is where my cursor is. And you can see that where the star appears to be moves. And so the answer is black holes. They change the apparent position of that background star and also change its brightness. Okay, so now the question is, does this actually even happen? Can we actually observe this or not? Or is this just, nice theory? And we can. And so that's the really cool thing. So this is a bird's eye view of the Milky Way galaxy. This is Earth, roughly here, kind of out in this neighborhood. It's not in the middle. In the middle here is where there's the highest density of stars. And this is called the galactic bulge. And so this is a bird's eye view of what would happen if Earth were here, we look through. This is actually what we see when we look up at the sky and see the Milky Way. So if you lived somewhere really dark, you looked at the sky, this is what you would see. This band of brightness, that's if you were here and are looking in this direction. And then the reason why there's kind of this like black stuff over here, this is dust in our universe. And so if you take a telescope and camera and you take a picture of this region, this is what the sky looks like. All these little these little dots, these are all stars. It's really, really, really crowded. And that means there's a lot of objects there. And the trick that I showed you before in that video, it depends on if you want to find an object in the front bending like something in the back, you have to have a lot of things crossing in front of each other by chance. And so even somewhere as crowded as the sky here in the Milky Way towards the galactic bulge, the chance that one of the stars in the background will have its light bent by something coming in the front is only 1 in a million. Oh. And so surveys observe, there's some telescopes on Earth that survey this region of the sky, surveying millions of stars, and they actually can detect these lensing, these light bending events. And so one of these telescopes is called the Optical Gravitational Lensing Experiment, short for the OGLE survey. And they just observed the galactic bulge the entire year. And this is some example data where these are stars, and usually they're not, this is brightness versus time. And so most of the time they're just, constant brightness, but suddenly they'll brighten and dim. And that's the signature of light bending events. And so these are 3 examples. You can see it's nothing's happening, and suddenly there's this brightening. And it's due to objects moving in front of background stars and making them brighter. But the last tricky thing is what's doing the magnification. Black holes are the thing we're interested in, but it turns out stars are also massive. And so they actually can also bend the light of other background stars. And so the question is, we see these brightening events, but which ones are due to black holes and which ones are due to stars? And there's actually a lot more stars than black holes in the Milky Way. And so most of these brightening events that are seen by these surveys are actually due to stars and not black holes. From this brightening versus time plot, which we call a light curve, we can't actually figure out what is doing the bending, whether it's a star or black hole. They'll produce the same looking signal. And the important part then is we can't just measure the brightness. We also need to measure that change in position of that background star to figure out whether something is a black hole or not. And so this is the project that I was been working on as a graduate student to identify one of these black hole candidates and using measurements of the position, figure out whether it's a black hole or not. And so this is the brightness versus time data from this ground-based survey telescope called OGLE that I showed you in the previous slide to measure that brightening. And then this on the bottom, this is position measurements. And this comes from the Hubble Space Telescope, the one that's Earth, orbiting Earth. And Hubble Space Telescope is able to very precisely measure the positions of stars. And so we were able to use this telescope to get, this telescope got data on this particular brightening event and measure the position of that background star as it was getting bent. And so this is showing in one direction versus time, and then the other direction versus time, and how it looks on the sky. And so because you can see a slight change in the position of the star, it wasn't just moving in a straight line. We call that the astrometric deflection. The astrometric deflection combined with the brightening in the light curve allowed us to measure how big that object bending the background star's light was. And from that, we're able to figure out that indeed there was either a really massive neutron star or a low mass black hole that was bending the light of the background star. And so this is how we can find isolated black holes. So yeah, thanks for listening, and happy to do any discussion or questions or things like that.
So this event happens just once, so it's all kind of recorded with the telescope, and you have to go search for them in the time scale or something.
That's right. It only happens once, and so this is what's called a transient event in astronomy. So it's it doesn't repeat. Once it's over, because once the past by, and then it's over, and then they just keep moving apart forever.
But the events are being recorded, right? So you can play it back anytime, pretty much. If you want to search back and find instances like that.
That's right. So you can go back and look in the data. The problem is if you want to try to measure its position, it's happening as the same time as the brightening. And so the trick is that there's slightly different time scales. The change in position happens for a longer time than the change in brightness, but you can't wait too long, because otherwise the position isn't changing anymore. It's because they're so far apart that essentially the light from the star won't be bent anymore.
Oh, so the trick is, Hubble may not be looking at that star at that time, or do you have to kind of turn Hubble to look at that star very quickly once you detected that event that you suspect is going to be a black hole?
Yeah,
so that's pretty tricky, because as you said, there's a lot of these brightness changes that could be caused by star on star. So you have to catch the right one, and then get time on a Hubble to go to look at the position change, right?
Yep, exactly. You just summarized the entire project, exactly what happens.
That's very hard. That's very hard.
Yeah, so this data was...
So let me ask, how many of these brightness events that you detected that you went to Hubble to look at position and find out it's not a black hole or just a star?
Yeah, so this experiment has been done by several people. So this is archival data we looked at. And so somebody proposed to look at they looked at 5 different brightening events, and then only this one out of those 5 events turned out to be a black hole.
Okay. So you did a sampling. Okay.
Yeah. So another project. So I talked also a little bit about the Keck telescope earlier. The project led by my advisor, Professor Jessica Liu at Berkeley. Like, we tried doing the same thing. And so, for example, she did several years ago an experiment looking at 3 objects, and then at 3 objects, it turned out none of those were black holes. And so, yeah.
So it is you need to be very patient and take a lot of effort to find one.
Yeah. So the thing
sometimes by a luck, a stroke of luck,
Yeah, there's definitely luck involved, because we know the best way to select the candidates so that the chance of being a black hole is high. But even when we do that selection, it's still typically 30-40% chance for any one object will turn out to be a black hole. So if you just picked at random, it'd be 1 in 100, but we can do a better job in selecting. But even when we do that, it's still only about 30%.
Casey, you mentioned something that I didn't quite understand. I understand that stars don't move in terms of perspective. And then you said the black hole is actually a dead star, but you also said that it moves.
Oh,
right?
I see.
Black hole can move.
Sorry, I meant actually stars and black holes, they're all moving in the universe. I meant in this animation specifically.
Okay. So
Yeah.
so from our perspective, they move because the Earth's rotation when we observer moves or the star moves.
I see. Yeah. So the Milky Way galaxy, where did that slide go? All the stars are rotating.
Okay. All
And then
right.
so it's a perspective event. So Earth is also orbiting around the galactic center, and all the stars are also orbiting. But there's also random motions from these stars. They're not all exactly moving at the same rate. They're also scattered, moving in kind of, there's random scatter. And so all those motions together are what cause sometimes things to cross in front of each other.
Got it. Thank you.
You mean your discovery was publicized quite widely in the press, and I saw a comment that there were another group somewhere on the East Coast that was looking at the same star and was trying to have a competition, maybe, or whatever. What is that?
Yeah, so there's another group that was also looking at this object, and so this data is really old. So some of this data was first taken back in 2009,
Oh,
and so this is archival data. So
yes.
yeah, so they originally took the data and then looked through it, and then we decided to take a second look through it, and then this is when we found this object, and then so after that, when we thought it was interesting, we took additional Hubble data more recently in 2021 and 2022 to better understand the motion of the star. And so we find something slightly different from them. We get a different mass measurement for that lens. Yeah.
So you went and used Hubble look at the star to see what it is doing without the black holes to compare it when the transition was happening. Is that to get a more accurate position change?
Yeah, because the position change happens over such a long time scale. It happens over years. So this first data point, it's a little bit hard because the axis here is time. This first data point is from 2011, and then this last data point is from 2021. So there's 10 years between here.
Okay, so the dot shows where you're taking the data.
Yeah. So the dots here are the data.
Okay.
So there's about 10 measurements here. This is 2011, and then this is 2021. And then this is also, each bar is a data point. And this is data from 2010, this is 2011, and then this is 2010, 2011, 2012, and then there's more data, but we didn't show it in this particular figure because after that it's just flat. But
okay.